this series of playlists will talk about Nyquist stability criterion. Alright, Nyquist stability criterion. And if you were to type plus an example in the Google, alright, if you were to type this thing in Google, the first link will come out. And this is where I will refer to in the rest of this playlist. Okay? And therefore, in order to start this playlist, I'll just start off with the concept of mapping. Okay? I'll not talk about truly the meaning of mapping just yet. I'll just talk about the definitions of S. Okay? So in order to start, I'll talk about the meaning of this one and the meaning of this one first. Okay? And therefore, if you were to remember back, the S is comprises of the real axis and the imaginary axis. Alright? If you were to take a look, this is the real, this is the imaginary. Alright? And that's all. S is simply any point at the real and the imaginary. Can be this point, can be this point, can be any point. Alright? It's just specifying the space in the S space. That's all. Alright? It's just simply as that. And I know that the real axis can be re-represented in terms of a Pythagoras theorem. Right? We have an angle over here, and this is simply the real axis, which is also considered as cosine theta. And the magnitude, alright, the magnitude, this is maybe 5, this is 6. The magnitude is simply times 5 or times 6. So this is some constant, so I can just simply write as r cosine theta. Right, that's all. So r is just some magnitude times the cosine theta in the real axis. This whole thing is still in the real, or in other words, this whole thing is simply this one, that's all. Alright, I'm just trying to re-represent sigma, this real axis, as r cosine theta, that's all. Okay? And this j omega is simply sine theta. And likewise, the magnitude itself can be here, can be here, can be here. Anywhere on this imaginary axis is all determined by how many multiplication or how many times you scalar it. I will call this r also, which is r sine theta j, because it's in the imaginary axis. And therefore I can re-represent the real and the imaginary as r cosine theta, where this is simply this one, okay, plus r j sine theta. Alright, because this is the real and this is the imaginary, and you just simply give you the point at a certain point S, which is in the S, which is this one. Okay, and therefore this we can re-represent this cosine theta and j sine theta as e to the power of j theta, while the constants are simply r. And there we derive our Euler's formula. You can search Google to it. Alright. Therefore I can re-represent any S point. I can re-represent any S point in terms of the y-axis and the x-axis. I can re-represent any S as rej theta, as this one. Right? This is a magic formula right now. And therefore, this is why I represent S in terms of 5ej theta, where 5 is simply r. Okay? So this is our stuff right now. The next understanding that I want to highly convey is the concept of why do I take, alright, this is the theta over here, alright, which is also the theta that I've drawn in this portion right here. Why do I take theta from 0 to minus 2 pi? Why do I take theta to plus 2 pi? Why do I do that? Okay, if you remember, alright, not remember, but if you take a look, if I have a response, alright, this is some rej theta, alright. If I run from 0, if I sub in r theta as 0, I will just simply have a magnitude of r over here. This is just r. Okay, this is the function of this. Okay, maybe I should rearrange. Okay, Rej theta is simply the function of a curve, the exponential curve decay. Okay, and not decay first. Okay, no, we don't talk about it first. If I sub in theta as 0, I'll have r, right? E to the power of 0 is simply equals to 1, and 1 times r, because this is 1 now, 1 times r is simply r right now. And therefore, now if I were to sub in minus 2 pi, alright, I'll have re minus 2 pi, which is this one will become 0. Alright, when 0 times r is simply 0 over here. For example, this is minus 2 pi, and then this is minus pi, and this is 0, for example. And you'll get an exponential curve that decays, and this is simply Rej theta when 0 towards minus 2 pi. Okay, this is the definition. But what I want to convey more importantly is that this curvature right here is going into 0, right? Its final value is 0, and therefore we can say that this is stable. This is why we want it to decay. We want to introduce a minus so that the exponential will eventually become 0. On the other hand, if I were to sub in, alright, if I were to sub in plus 2 pi, alright, when r is equals to 0, alright, when theta is equals to 0, okay, we know that this is simply at this point right now. And if plus 2 pi, alright, from 0, this is pi, this is 2 pi, then you're gonna have a curve that is going in this manner. You're gonna go into infinity, which is unstable. And we are not interested in the unstable region, we are interested in whether how things are stable. And this is why I use 0 to minus 2 pi. Okay, I hope this is pretty clear much. And therefore, since we know this one and this one clearly, then we can just plot already. We can plot 0 and minus 2 pi into our Euler's formula, which we derive in terms of the S is equals to sigma plus j omega. Alright, and this is pretty much important. Therefore, if I were to sub in as 0, I would have cosine. If cosine 0 is simply times 1, right? And then cosine 0, sine 0 is simply 0. And therefore, I have r plus 0 in the imaginary axis. And we know that r is simply 5, right? And therefore, we are plotting it onto this point. And along the way, you'll just plot in the clockwise direction. You see? For example, if you don't believe me, I'll just crop out the data that I've done. Okay, I'll just crop it over here. You see, this first row is simply what we have done over here. Alright? So the subsequent value when I put in, alright, for example, this is 0 degrees. Subsequently, I put in minus 20 degrees, and I change to radian and cosine it. I'll have minus 4.69 and minus 1.71. If you take a look, minus 4.69, right? Minus 4.6 is somewhere here, or it's somewhere here, and then minus 4.69 is somewhere here. Okay, and then maybe I should pull this thing all the way down. Okay, and then minus 1.71. Minus 1.71 is the imaginary axis, right? So minus 1.71 is simply here. So this is the point. So as you know, so this is one proof of the data that you will eventually go to the clockwise, and is being used with the understanding of the Euler's formula. Alright, and this is the first definition of z, or the 0, is going in the clockwise direction. Why? S is simply a 0, right? If the transfer function, for example, a transfer function, right, is simply g of s is equals to s plus 1 over s plus 2. For example, this is a transfer function, right? The numerator is simply the 0, the denominator is simply the poles, correct? And therefore, transfer function now is equals to s. It's just a pure 0. and therefore we can just say that it's a clockwise direction. Since we have just proved that S is simply going in the clockwise direction, you know. And therefore the first takeaway from this video is that the 0 is turning in the clockwise direction. And in the next video we'll talk about how does this S, or the concept of this ej theta, is being applied throughout all the stuffs in the other transfer functions. I shall see you there.